This webcast continues talking about energy pie charts, and so we're working in worksheet 6C. And the next problem involves a wind-up robot walking across the table and coming to a stop. So I couldn't find a video of a wind-up robot, but I have a video of a wind-up kitty cat here. So let me just let you watch the cat get wound up and move. Okay, so when the little toy is wound up, it can move, but it gradually slows down, right, and will eventually stop moving. So when he's fully wound up, and we're going to say not moving yet, okay? So maybe we're holding the little robot in our hand, but we have wound up the spring inside the toy. And so by winding up the spring, we have changed its shape. It's been deformed, but it's a temporary deformation, right? The spring will unwind when we let it go. And so it is storing elastic potential energy. And then we see the toy walking across the table, and it slows down. And also, did you notice that the little kitty cat's feet were rubbing against the table? So I think there's some friction because, you know, the feet were rubbing on the table. So we have some kinetic energy here because it's moving. We have some edus because whenever you have to overcome friction, some energy gets dissipated, right? It goes into that storage mode where it is unrecoverable and unusable, microscopic kinetic energy. It's just his little feet and the table heating up a little bit, but that's no use to us. In this kind of toy, unlike the pop-up toy, which we saw before, in the pop-up toy, as soon as the toy pops up, the spring is relaxed. It's back at equilibrium. But in a wind-up robot or any kind of wind-up toy, the spring goes back to its original shape over time. And so we're still going to have some elastic potential energy in the middle here, because as long as it's moving, the spring still has some deformation. But it is moving, and so there is some kinetic energy. And then also, because of the feet rubbing on the table, overcoming friction, some energy is stored as dissipated energy. The sizes of the pieces of the pie that I'm drawing, you might choose a different way to draw your pie, and it could still be just as correct. What's important is to show the correct trends and the correct types of energy storage. So when I talk about trend, initially all of the energy was stored as elastic potential energy. Less of it is elastic potential energy in the second view at position B, right? Because by position B, since the robot is now walking, some of the elastic potential energy has gotten moved to kinetic and dissipated energy, okay? But again, the specific division or pieces, the sizes of the pieces of the pie, you might do them a little differently from me, and that would be okay. Okay, at some point, the robot stops moving. So there's no more kinetic energy if he's not moving. There's no more elastic potential energy by that point. That's the reason he stops, is the spring has gone back to its original shape. And so by this point, all of the energy that was originally in the robot is now dissipated energy. I'm just going to keep going because the more examples we do, the easier it is to understand. Here's a ball rolling across the table and coming to a stop. So when we first look at it, and this is after it's been given a push, so it's moving kind of fast, in part A. And then it slows down, and eventually it stops. It's on a table, so the height doesn't change. I'm going to go ahead and draw my circles, the pies, right? So because since this is an isolated system, there's no energy transferred in or out of the ball plus the table plus the earth, then the amount of energy should stay the same. So initially, it's moving fast. And so I'm going to just say that all of its energy is kinetic energy. There's maybe an important thing to say here, which is that you never show dissipated energy in the first view. Okay, that's very important. So because we haven't seen it go anywhere yet. And so, let's see. I want to make that red. Okay, so that's just an important general type of note. And so therefore, since at position A I haven't seen the ball move anywhere yet, I'm going to not show dissipated energy yet. But the reason that it slows down is because there is a friction force on the ball, right? It is rolling across the table. And so the reason it slows down is because gradually some of its energy that was originally kinetic energy is getting moved over to dissipated energy, right? And that redistribution of energy from kinetic to dissipated explains the physical thing that we're observing, that change of its speed. It was going fast and now it's slowing down. And at the end, when it has stopped, it has no more kinetic energy. At that point, all of its energy has been dissipated. Okay. 5, the rabbit that's wound up fully, but we're still holding it, not letting it move, it's just storing elastic potential energy. Okay, but let's go on to 6. Here we've got a little wind-up toy, this little rabbit, and it's moving across level ground. These arrows are meant to be velocity vector kind of thing. So in this example, the toy is speeding up. If it's speeding up, that tells me that the kinetic energy is increasing, right? Because I recognize kinetic energy by looking at how fast something is going. So I'm going to choose, 3 places here because I want to show how the energy redistributes. And so I'm going to show 3 pies. At the beginning, the rabbit is just barely starting to move. See this little arrow here? Mostly it's just wound up. And so I'm going to show just a little sliver as kinetic energy and the rest of it as elastic potential energy. I'm not going to show dissipated because I have not yet seen it move anywhere. You never show dissipated in the first view. Okay? In the second pie, though, the little rabbit's feet, they've been rubbing on the table, and so there is going to be some dissipated. Let me just go ahead and show some dissipated because he's been overcoming friction as he moves, but he's speeding up. So I need to show more kinetic energy than I had in the first view. And the spring is gradually unwinding, and so I need to show less elastic potential energy. Okay? And then at the last view, it's even faster. And there's even more dissipated energy because he's gone further. But there could be very little EEL at this point, right? The spring is starting to be to go back to its original shape. So there's more kinetic energy. So the kinetic energy piece of the pie is bigger because he's speeding up. There's more dissipated energy because he's overcome more friction, and elastic potential energy is getting smaller and smaller. So again, you might draw your pie piece is slightly differently than mine, and that's okay, but you've got to show those trends. We have to show elastic potential energy getting smaller, kinetic energy getting bigger, dissipated energy getting bigger. Okay. Let's look at number 7. Here we have the rabbit. It's wound up. It's moving at a constant speed up an incline. Okay, so let me choose, 3 places here, and I'll show 3 pies. So there's A, B, and C. And at A, I'm going to say he's on the ground. At the very beginning, he's on the ground. So the height is 0 at A. So since the speed is constant, I need to just choose a size of the pie and have every pie have the same amount of kinetic energy, right? I recognize kinetic energy by the speed, and since the speed is constant, the kinetic energy of the rabbit should be the same. Now at the beginning, the toy is fully wound up, and they're on the ground. So if they're on the ground, there's no gravitational energy yet, but there is a lot of elastic potential energy. Now, as the rabbit moves up the hill, here's the hill, right? It's a steep hill that he's going up. His feet are rubbing on the ground, so I'm seeing some dissipated energy because he's overcoming friction. And as he goes further, the dissipated energy should increase, right? But I don't show dissipated energy in the first view. That's a rule. His height is changing. At the beginning, he was at height 0, but at B, I don't know, he's higher, right? And at C, he's even higher. So we have some gravitational potential energy here. And it gets bigger as he goes up the hill. And what's happening to the elastic potential energy? It's getting smaller, right? In fact, up here it's got just this very little sliver because the spring is gradually going back to its original shape. And so there's less and less elastic potential energy. At some point he'll have to stop because the spring will be back to its original shape. Okay. And I want to do the last 2 for sure. So in number 11, we have a battery-operated car. Now, we don't deal with this a lot, but a battery implies that there is chemical energy. And so it's another way of storing energy. It's a different storage mode. And I represent that with an E with a CH subscript. Okay, so the car is going at a constant speed. I'm just going to do 3 circles. It's like A, B, C. Okay. Since it's going at a constant speed, I'll just choose a portion of the pie and make it the same because kinetic energy is going to be the same since the speed is the same. Now at the beginning, I'm not going to show dissipated energy because I never show it in the first view, but the batteries are fresh. There is a lot of chemical energy. Notice that the height of the car is not changing, so I'm not going to make any mention of gravitational potential energy since there's no change in height. But what is happening is the tires are rubbing along the ground, so dissipated energy keeps growing. And as dissipated energy grows, the chemical energy declines. And we have not stopped. No, I'm good. We have not stopped here, and so there's still some energy in the batteries, but it's smaller. Okay, and then I also want to do 12. This is an important one. A ball bouncing up and down. This is a rubber ball. And you know a rubber ball bounces, but it doesn't ever come quite up as high, right? Each of the bounces, like there's where it was when I held it in my hand. It hit the table, and then here's the first bounce. It's not quite as high as it was from where I dropped it. And then on the next bounce, it's even lower. And then on the next bounce, it's even lower. And it just keeps, the height of its bounces is smaller and smaller until eventually it is motionless on the ground. Okay, so the locations have already been labeled for us, A through F. And so I'm going to draw that many circles. Okay, so these are to show how the energy is distributed at those locations. Okay, at the beginning, the ball is very high in the air. I'm holding it up, but it's not moving. And so there's no kinetic energy since it's not moving. And a rubber ball, there's no, its shape is normal right there. So really the only kind of energy it has at the beginning is gravitational potential energy because it's very high. Then at position B, it's at the bottom of the first bounce, and it's not moving for just an instant. So there's no kinetic energy, there's no gravitational energy. Now it's on the ground. But what happens when the ball hits the table? It deforms a little bit, and it happens so fast that you may have to watch closely, but it deforms, and it's a reversible deformation. The ball presses in, and it's going to bounce back to its original shape. But not all of the energy becomes elastic, is stored as elastic potential energy. There is a little bit that gets dissipated. And it's dissipated because when the ball hits the table, it heats up the surface of the ball and the table, and that's that unrecoverable, unusable, microscopic kinetic energy, right, from just heating up the ball and the table. Okay, so a little bit of energy gets dissipated. Then, at position C, we're at the top of the first bounce. So we're looking at it here at the peaks, if you will. So there's no motion for an instant. So I'm not going to show any kinetic energy. In this path, as it's traveling up in the air, there's no more dissipation, okay? So the dissipation here is the same as it was at position B, because we only dissipate some energy when the ball hits the table. But the ball has gone back to its original shape. It's not deformed anymore. Now it's up in the air. And so there is gravitational potential energy. This slice of the pie that is EG is smaller than the amount of gravitational energy at position A. And that makes sense, right? Because it didn't go as high, and so therefore less EG. Position D is at a second bounce. So here, when it hit the table, before it got up here, it dissipated more energy. So now I see the dissipated energy growing, and so EG is even less, right? Okay. And then finally, let's see, at position E, now we are falling. Oh, my yellow highlighting has confused me. I'm sorry. Position E, we are falling. And so it is moving downward. It's not quite as high as it was at D, but now it is moving. No more energy has been dissipated, because remember, dissipation only happens when it hits the table, and it hasn't hit the table since we showed the energy distribution at D. But it doesn't have as much EG because it's lower. So I have less gravitational potential energy because it's lower, But now I'm going to show some kinetic energy because it is moving. Okay, so there's kinetic energy. And then finally, we get all the way over to F, where it is motionless on the ground. By that point, all of its energy has been dissipated.